Okay, so I hope everybody had a nice restful break. Just a couple of reminders here. Your gravitation assignment, okay, is due on, what is that, Thursday? No, yeah, Thursday. Okay, so make sure you've got that gravitation assignment done. If you miss getting a copy of that, talk to me after class and I'll get you your copy. And then rest of the semester is going to look like this. You are going to have a unit exam for Unit 4 somewhere around or on January 21st. Okay, that is when I aim to be finished the course. Okay, obviously you don't have a final exam, and obviously that's a little bit before the semester is over. Okay, a couple of days. Mr. Dickey and myself are still figuring out when we want to do our mock final, so I will have that detail ready for you this week. Okay, remember that the mock final is optional and no fault. Okay, if you A, don't have to write it, and B, if you do, it can't hurt you. Okay, what it can do, if you do well enough, is it can replace your lowest unit exam mark. Okay, so that is entirely up to you whether you choose to write it or not. Okay, the option is available. Now, the caveat to the mock final. You are only eligible to write it if all of your assignments are submitted. If you have any zeros because you didn't submit something that wasn't exempted, okay, if you came and talked to me and I exempted something, that's different, okay? But if there's anything that's actually in as a zero and counting as a zero because you didn't do it, then you are not eligible to write the mock. Okay, you have to have everything done to write the mock. That's the only caveat. Okay, so that's where we're heading. Okay, aiming to be done by the 21st. Okay, so today we are going to start simple harmonic motion and waves. This unit is kind of 2 units pushed together. Okay, but they're done that way because simple harmonic motion is usually what causes waves to form. Okay, so they're very closely related, okay, concepts. So we're going to look at what is simple harmonic motion, how it can happen and be maintained, and we're going to look at 2 common examples of simple harmonic motion, a mass on a spring and the pendulum. Okay, we've talked about the pendulum already from a conservation of energy point of view, and we'll still look at it from that point of view, but we're also going to look at why does it go back and forth. Okay, what are the things that make a pendulum swing across over the same path over and over again? Okay, everybody with me there? Okay. All right, then, if you ever swung on a swing as a kid, okay, you were undergoing simple harmonic motion. You were essentially a pendulum, okay, and you were swinging back and forth. Okay. In order to get simple harmonic motion to start, do you have to do work? Right? Either mom or dad has to give you an underduck, or you've got to pump your legs, okay, and get that thing going. But once you get it going, okay, you can stop pumping and you'll just swing back and forth. I mean, obviously it slows down because it's not a perfect system, but you swing back and forth with simple harmonic motion, okay, pretty easily after that. Okay? If I bungee jump, okay, if you're a bungee jumper, you're a mass on a spring. The bungee cord is an elastic object like a spring. Okay? And if I throw myself off of a bridge with that attached to me, okay, then as soon as I start to stretch the rubber band, am I doing work on it? Okay? And I don't know if you've ever watched someone after the exciting part, okay, but they bob up and down like this on the end of the bungee cord for a while because they're a mass on a spring. Okay? The energy that stretched the spring was the potential energy they had from being on the bridge, okay, and then jumping off. All right, everyone okay with that idea? Okay, so there's going to be a little bit of new terminology today, okay, some things to do with simple harmonic motion that we haven't measured or talked about before, okay, but a lot of it is going to seem familiar as well. Things like period and frequency, okay, things like that are still going to be the same, still have the same meaning in this unit. Period is the time for one cycle, okay, so for a pendulum, okay, the period of a pendulum is how long it takes to go from this position through one cycle and back. Okay, that would be measured in seconds. How many times it does that per second would still be the frequency. Okay? Now, what we're also going to find is that a lot of musical instruments rely on something oscillating back and forth with simple harmonic motion to produce sound waves. Okay, so whenever you pluck a guitar string, you're doing work. You're exerting a force through a distance on that string. It's elastic. It wants to go back to its original shape. So when you let it go, it vibrates back and forth, okay, moving the air, pushing on the air around it and creating sound waves. Okay, but it oscillates back and forth, okay, over a common path with simple harmonic motion. Okay. All right. Oh, sorry, something I forgot to talk about. So there is one new piece of terminology here, okay? And that piece of terminology is this, the equilibrium position. Okay? Anything that oscillates with simple harmonic motion has an equilibrium position. That is where the object would be if it was at rest. Okay, so for a pendulum, where's the equilibrium position for a pendulum? Where would it be if it was at rest? Right there, right? Is that where it would be when it's at rest? Right, because up here, is there a force acting on it? There is. Okay, here, not as much, right? I mean, gravity still wants to pull it down, but let's say it can't fall any further than that, okay? There'd be no net force acting on it here, okay? At the equilibrium position, any object that is undergoing simple harmonic motion has no net force and no acceleration. Okay, so when you pluck a guitar string, okay, before you pluck it, it's at its equilibrium position. When you pull on it, you exert a force through a distance, moving it away from the equilibrium position. The elastic nature of the guitar string tries to pull it back to equilibrium. Okay, when I move the pendulum away from its equilibrium position, gravity wants to pull it back there. As soon as the object moves away from equilibrium, there are now forces that want to bring it back. Okay? Forces that want to restore equilibrium. Okay? Any force that wants to restore equilibrium is called, wait for it, a restoring force. Once in a while we keep things simple. Okay, so a restoring force wants to restore equilibrium. So for a guitar string, it's the elastic nature of the guitar string. It pulls the guitar string back to its equilibrium position. Okay. For a bungee cord, it's again the elastic nature of the bungee cord. It pulls the person back to its equilibrium position, okay, the position it would be at if the person hadn't jumped off a bridge. Okay. For a pendulum, gravity wants to pull it back to the middle to its equilibrium position. Now, here's the thing about simple harmonic motion. All simple harmonic motion requires a restoring force. Okay. I mean, if this is going to oscillate with simple harmonic motion, it's because there's a restoring force always trying to pull the pendulum back to equilibrium. Okay? Now, the other thing that has to be true is that force has to increase with distance. Okay? Think back to Science 10. Remember doing the lab with the rubber band around the chair legs? Right? We pulled it with a spring scale. Okay? What we were measuring there was the amount of work that was being done on the rubber band. What we didn't realize is that force we were measuring on the spring scale was the restoring force of the rubber band. The rubber band wanted to go back to its equilibrium position. If we'd have let go of that spring scale, okay, it would have shot the spring scale and the rubber band would have vibrated or oscillated back and forth with simple harmonic motion for a short period of time. Okay, so restoring forces are necessary for simple harmonic motion to occur, and they have to get bigger the further from equilibrium you go. With a rubber band, it's obvious. The further you stretch a rubber band, the harder you have to pull. Okay? If you're trying to compress a spring, right? If you push on the spring a little bit, it'll compress a little bit. But if you want to make it to go further, you have to push harder. Okay? So for simple harmonic motion to occur, the restoring force has to vary linearly, that is, increase linearly with distance. Okay? All right. Okay, so in each case, there is an equilibrium position. Whenever it is pulled away from the equilibrium position, a force in that system pulls it back to equilibrium. That force could be gravity, in the case of a swing or a pendulum. Okay, it could be the stretch of a guitar string, string, or a spring. Okay, so in the case of a mass on a spring, okay, this is the equilibrium position. That is where that thing would rest. If I want it to oscillate, I've got to push it this way. Now, if I push it to the left, which way does the spring push? To the right. Okay, that's the restoring force. It wants to make that mass go back to the equilibrium position. Now, if I let it go, will the restoring force succeed in restoring equilibrium? For an instant, yes. Why only for an instant? Okay, my pendulum is at equilibrium. If I disturb it away from equilibrium and let it go, the restoring force pulls it back to equilibrium, yes? But then what does it do? It overshoots. It overshoots every single time. That's the only way you get a repetitive harmonic motion, is if that restoring force constantly succeeds and fails. Okay? It succeeds in restoring equilibrium for an instant and then goes right past it and has to reverse. Okay? Because once this pendulum goes through the equilibrium position, now gravity's got to try and pull it back. Okay? And the spring's going to do the same thing. If I push this thing in and let it go, that mass is going to oscillate back and forth. The spring is going to constantly try and restore equilibrium and constantly fail. Okay? It's going to go right through equilibrium and have to pull the other way. Okay? Everybody following me on that? That's, of course, assuming there's no friction, right? Because friction would eventually make the system stop. This is an ideal system where that thing would oscillate forever. Okay? You put that energy in, energy is conserved, it'll oscillate forever. Okay? All right, everybody good with that? Okay, now obviously with a mass on a spring, okay, it makes sense that the harder I pull on the spring or the harder I push on the spring, the harder the spring pushes back. Okay, that makes sense. It's a linear thing. A pendulum uses gravity. Does the force of gravity get bigger? Force of gravity acting on this tape any bigger here than it is here? Tape weighs the same amount here at equilibrium as it does out here. Didn't we just say this was an example of simple harmonic motion? And for simple harmonic motion to happen, the restoring force has to vary linearly with distance? Well, if I'm relying on gravity and gravity doesn't get bigger, how does that work? Well, which way does gravity pull?
Straight down.
Straight down. Which way does this tape go when I let it go? It swings along an arc, like this. Okay? So, it's not gravity that's the restoring force. It's the component of gravity. Okay? Gravity wants to do this, right? But the string prevents it from falling. So, there's a component of gravity that acts along the arc. The further from the equilibrium position you get, the closer to the full force of gravity that part that acts along the arc becomes, okay? When the ball is right here, okay, or when the tape is right here, that little bit of gravity is only that big, okay, because the angle is very small. Over here, the angle is a lot bigger, okay? So it's actually not gravity that's the restoring force, it's the component of gravity along the arc. And that does get bigger linearly the further away from equilibrium you get. You are never going to be asked to tell me that in any way, shape, or form. I'm just making sure you understand that this is still simple harmonic motion, and that whole restoring force varies linear thing still happens. Okay, because a lot of people get hung up on gravity doesn't get bigger. You're absolutely right. But force is a vector quantity, and because of this string, there's another force. This is like net force. Okay, there's gravity acting straight down, and there's the string pulling this way. Okay, those act in concert to produce a net force along the arc that does get bigger the further away you get. Everybody okay with that? You're never going to be asked to do vector addition in this unit. Okay, just as long as you understand that's why. Okay, so write this down. This is the fundamental piece that explains simple harmonic motion. Okay, for simple harmonic motion to occur, the restoring force must vary linearly with displacement from equilibrium. Okay, so any situation where this can be true, a guitar string, a pendulum, mass on a spring, bungee cord, whatever, okay, simple harmonic motion can be produced in that situation. Okay, now, thinking back to something from Unit 2, work energy theorem. Okay, if I stretch a spring, am I exerting a force through a distance? So I'm doing work, agreed? What am I putting in the spring? Potential energy, yeah. Elastic potential energy, okay? But I'm putting that in there. And when I let that object go, that potential energy will be converted to kinetic and the thing will oscillate and obey the law of conservation of energy. Okay, everybody all right with that? Okay, so we are going to look at, maybe not today, we'll see if we get to it, okay, the different types of potential energy. Up until now, we've only ever done any calculations with this, okay, gravitational potential energy, but in this unit, we're going to be dealing with this one. Okay, that's the formula for elastic potential energy, and it actually is a derivation of this one. Okay, because X, for whatever reason, don't ask me why, stands for displacement in that formula. Okay, displacement measured from equilibrium. That's why it's a different letter. Okay, K is the stiffness of the spring, something we call spring constant. Okay, you've probably noticed that not all springs are the same. Okay, like the spring that's in a clicker pen is very, very different than the springs in your car. Okay? The springs in your car are much stiffer. They have a much higher spring constant. That means it requires way more newtons to change their shape by 1 meter as it does the little clicker pen spring. Okay? Everyone with me there? So K is how stiff is the spring. Okay. All right. Questions there? Okay, so talking about things we've talked about before, period and frequency. Okay, those still mean the same thing they meant before. Period is still the time for one oscillation. Frequency is still the number of oscillations per second. Okay, we will be using slightly different units for frequency. Okay, frequency is measured in hertz. Okay, which actually is an abbreviation. It's a person's name, but it stands for oscillations per second. Okay, so Hz is oscillations per second. Period will still be measured in seconds. Okay, this is a new term, amplitude. Okay, amplitude describes how far, the maximum distance from equilibrium that the oscillating object will go. Okay, so does anyone have a big stereo in their car with an amplifier? Okay, all right. So what does the amplifier do? Makes it louder. Okay, how does it make it louder? What does it make the speaker do? Yep, further. Okay, if you just hooked a subwoofer up to a regular stereo, it would do this. It would hardly move. Okay, but if you want the kind of bass in your car that basically gives you a massage when it's on, okay, and you're driving down the road and you're going like that guy who drives down my street all the time, okay, you need an amplifier. The amplifier makes the cone of that subwoofer move further. Okay, the further it moves, the louder the sound. Amplitude has to do with energy. Okay, the greater the amplitude, the greater the potential energy of that oscillator. Okay, in a speaker, that's actually done with a big magnet. Okay, if you've ever noticed, there's a big round magnet on the back of a speaker. Okay, when the electricity goes in there, the electricity just pulses the magnet. And the magnet will pull the speaker cone back and then let it go, or actually power it forward. Okay, and that creates the compressions that you can hear and feel, okay, from a subwoofer. Okay, the more you crank the dial to the right, okay, the more power goes into that and the further that speaker moves. It doesn't actually move any faster. It just moves further. Okay, so it moves further and it makes those compressions and rarefactions that we identify as sound. Okay, it makes our eardrums move back and forth. Okay, we have to be careful with that. We don't want our eardrums to go too far. Okay, otherwise we won't hear as well later in life. Okay, so if we're looking at this mass on a spring, okay, the dotted line through the middle here is the equilibrium position. Okay, so let's say that we start here, and then this would be a vertical spring. So we let the mass go. Gravity pulls the spring or the mass down and stretches the spring. Okay, then the spring starts to win. Okay, and it's pulling now harder than gravity, and it accelerates the object back to the equilibrium position, overshoots it, as all restoring forces do, okay, and compresses the spring up here. Well, as soon as the spring starts to get compressed, it's starting to push back towards equilibrium, and will force the mass back to equilibrium, okay, and this thing will just keep oscillating back and forth over this whole path. Okay, everybody with me there? Okay. Look what happens when I connect the dots, because connecting the dots has this like reminiscent thing from when you're little. What kind of shape does that make? A wave. Okay, it makes a sinusoidal wave pattern. Okay, if this was, moving fast enough, it would create sound that we could hear. It would be compressing and rarefying the air. Okay, so simple harmonic motion results in a wave pattern. You can do the same thing with a pendulum. Okay, if you swing a pendulum back and forth and you put like a marker on it and then just hold paper, okay, and pull the paper past it as it oscillates back and forth, it does the same thing. It draws a wave. Okay? All simple harmonic motion is going to create wave patterns. Okay? All right, things we have to know about the nature of the movement or the movement of the object while it oscillates. Okay? At equilibrium, there is no acceleration at all because the spring is neither stretched nor compressed. That's where it would sit if there was nothing disturbing it. Okay? So it has no acceleration at equilibrium. So every time it goes through equilibrium, okay, we can see that the acceleration is 0. There's also no restoring force because the thing can't exert any restoring force until it moves away from equilibrium and either stretches or compresses the spring. However, every time you go through equilibrium, that is where your speed is at its maximum. Should actually say that here too. Why is the object going the fastest as it passes through equilibrium?
That has the most force being pushed by the spring.
Well, actually, the force is 0 at equilibrium. But has there been a force acting on it all the way there? Yes. Okay, so once it starts to move away from equilibrium, the spring is either pushing or pulling it. Okay, so there's an acceleration being caused by that restoring force. Okay, so if it gets out to here, okay, now it's accelerating back. Actually, it's accelerating back to equilibrium the whole way. Okay, but it's going back towards equilibrium, so it's going to go faster and faster and faster till it gets to equilibrium. And as soon as it passes equilibrium, it's going to start to slow down because now the spring is going to reverse and it's going to start to push instead of pull. That's going to slow it down as it travels to its maximum amplitude. Okay, so right here and right here, the object is at its maximum amplitude. And we use a capital A to symbolize that. That is as far from equilibrium as that object will go. How fast is it going when it gets there? 0. Because all the way there, what has the spring been doing? Pushing it back to equilibrium. So it's been slowing it down, slowing it down, slowing it down. Okay, so when you're at your maximum amplitude, the force and the acceleration are at their maximum because that's where the spring is either stretched or compressed the most and where it can push the hardest. It is also where you are not moving. Okay, because it has been slowing you down the whole way to the maximum amplitude. Okay, in terms of energy, what does that mean? What kind of energy do I have at the maximum amplitude here and here? Elastic potential only. What kind of energy do I have at equilibrium here and here? It's where I'm moving the fastest, so I would have kinetic. Think of it like a roller coaster, right? You're converting potential energy into kinetic energy. Equilibrium's where you're moving the fastest. It's like the bottom of the hill on a roller coaster. It's where you have only kinetic energy. Okay? Everybody all right with those ideas? Okay, so one new term here, okay, and that is amplitude. The maximum distance from equilibrium an object will get has a speed of 0 there. It has its greatest potential energy there, greatest acceleration, greatest force. Now, on the board is one complete oscillation of this mass on a spring. What would I call the amount of time that takes? Period. Okay, what two things could affect the period of this oscillation?
The weight or the mass?
The mass of that's on the spring and
How stiff the spring is?
how stiff the spring is. Those are the only two things, okay, that are going to affect the period of this pendulum. The spring and the mass you put on it. Okay, so that is where this formula comes from. Okay, this formula is on your formula sheet. It calculates the period of a mass on a spring. okay? And that is 2 pi times the square root of mass divided by spring constant. K is a spring's constant, how stiff the spring is. Okay, now I'm just going to write this so that it's not horizontal, okay? Because on your formula sheet it actually looks like this, which is how it should look. Okay, so looking at that formula and thinking common sense wise, if I increase the mass that's on the spring, will that make the period longer or shorter? Longer. Think about it. I mean, if a really small person bungee jumps off of a bridge and then a really heavy person bungee jumps off the bridge, the really heavy person is going to have a much longer period of oscillation because they can pull that string or that bungee cord further. It's going to take them longer to make that oscillation. So more mass means greater oscillation. Probably also means greater amplitude because it's going to stretch it further before the spring can slow it down and say, hey, come back. Okay? Now, what's the effect of putting it on a stiffer spring? Will that make the period longer or shorter?
Shorter.
Shorter. Stiffer spring's not going to go as far. It's going to oscillate quicker. Okay? That's part of why a guitar has different strings. Okay? Different strings oscillate at different frequencies. Okay? If you've ever tuned any string instrument, right, when you start cranking that thing and putting more tension in the string, it changes the frequency because you're basically making it stiffer. You're putting more tension in that spring and making it oscillate faster. Okay? If you back off, it oscillates and makes a lower frequency of sound. Okay? Okay. Questions on that? Is that going to be a fairly straightforward formula to use? Okay. If I want to solve for m or k, what am I going to have to do to everything before I do any algebra? Square it. I'm going to have to square everything to get rid of the root. Okay? People sometimes forget that, but I'll have to square everything to get rid of the root before I do anything else. Okay? Okay, so let's just have a look at this example here. So I've got a ball that has a mass of 200 grams or 0.2 kilograms attached to a vertical spring, and that spring's constant or tension is 28 newtons per meter. So spring constant always tells us, here's how many newtons you would need to make the spring 1 meter longer. Does that mean you can make every spring 1 meter longer? You cannot make the spring in your pen 1 meter longer. It's not that long, okay? It's just telling you, here's how many newtons it would take if you could, okay? It just has to do with the stiffness of the spring. Okay, the ball is released from its equilibrium position. How long does it take for the ball to complete one cycle and return? So, we're being asked to find period. We're told mass and K, the constant of the spring. Okay, so all I have to do is go T equals 2 pi times the square root of 0.2 kilograms divided by 28 newtons per meter. Okay, and if I do that, I should get just a little over half a second, 0.53 seconds. Okay, so if I'm punching that in here, okay, that's going to be 2 times pi times the square root of 0.2 divided by 28. 0.53 seconds. How would I find the frequency? That ring a bell from the last unit? We hardly ever used that formula, but we did learn it right at the beginning of the circular motion unit. Okay, T is 1 over F, F is 1 over T. So if they asked you what's the frequency instead of what's the period, calculate the period, go 1 over that number. We're going to get like 2 point something. Okay, everyone all right with that? Actually, sorry, less than 2, 1.9 something hertz. All right. Now, pendulum. Okay, pendulum. So, what can affect the period of this thing going back and forth? Only two things. What makes it go back and forth? Which force is making this thing work?
Gravity.
Gravity is acting as the restoring force. Okay, so would gravity have something to do with this? Okay, what else? Okay, watch this pendulum, and now watch this pendulum. Does the length of the pendulum affect how long it takes it to make an oscillation? Those are the only two things. Length and gravity. What if I put a heavier thing on the end of this? Would that change it? Why not, Josh?
I just don't think it would.
Okay, you're right. It won't, because all things fall at the same rate. G is the same for all of them, right? It doesn't matter how much weight is on here. Okay, if I had a wrecking ball, minus Miley Cyrus, okay, swinging back and forth, okay, it would have the same period if it was the same length as this. I wouldn't be able to hold it, obviously, but it would have the same period. Okay, everybody all right with that? Okay. So, for a pendulum, the formula is T equals 2 pi times the root of length over the acceleration due to gravity. This is actually one of the experiments that the Apollo astronauts performed on the moon. Okay? They took a simple pendulum with them, okay, and they tested what its period was on the moon, okay, as a confirmation of some of the numbers they were using to get them there. Okay? Obviously it wasn't a, whoo, we got here, now let's do the calculations. They already had good calculations, really smart people working at NASA. Okay? But they wanted to just do that, especially since on the moon there would be no what? Nope, there's still gravity, but it's a lot less. No air resistance. Okay? That pendulum would swing freely, okay, with 0 air resistance on the moon.
So would it swing forever?
No, because you still have the pivot point here. There's going to be friction there, right? Okay, so longer pendulum, greater or smaller period? Greater. Okay? All right, what if I increase the acceleration due to gravity? It'll get smaller. Okay? On the moon, this pendulum would go like this. Okay? Gravity's 1/6 of what it is here on the moon. So this pendulum would look really funky, okay, on the moon. Whereas here on Earth, it behaves exactly as we would expect. Okay? It does this. All right. Everybody okay with that? So, simple example here, okay? Now, terminology. The mass on the bottom of a pendulum is called the bob. Don't ask me why. I have no idea why. Okay, but the mass on the bottom of a pendulum is called the bob, the pendulum bob. Okay, so we've got this pendulum here, okay, that has bob. Plumb bob, square pants. That's the bob. Okay, apparently they're making a movie. Don't watch it. Apparently there are studies done that say you actually get dumber by watching SpongeBob. So, yeah, if you live in a pineapple under the sea. Okay, so we have a 1.5 or 1.55 meter long pendulum. Okay, gravity is 9.71 meters per second squared. Okay, we want to calculate the period, so we just punch in our numbers here. 2 pi times square root of 1.55 over 9.71. That pendulum would take 2.5 seconds to make one full oscillation. Okay, everybody all right with that? Okay, if I want to manipulate either of those two formulas, okay, so let's say I've got, let's Say I want to solve for L. What do I have to do to everything first? Square it. Okay. Okay, what do I have to do with G now? Multiply both sides by G. Okay, divide both sides by 4 pi squared. And I'm solving for the length of a pendulum. Okay, if I wanted to solve for G instead, come on. Okay, fine, you can play that game. Okay, if I want to solve for G, do I still have to square everything? Okay, so t squared equals 4 pi squared times L over G. Do I still move G over to this side? Yep. And now what do I do with t squared? Divide it over to the other side. Okay, so it's not a hard formula to manipulate as long as you remember you have to square everything in order to get rid of the root. Okay, I want you guys to try this one. Determine the length of a simple pendulum that will swing back and forth, simple harmonic motion, and have a period of 1 second, assuming regular Earth gravity. Okay, so what we're given in this one, we're told the period is 1.00 seconds. We're told G is 9.81 meters per second squared. Okay, T equals 2 pi times the root of L over G. We're trying to solve for L. So square everything. 4 pi squared L over G. Okay, multiply both sides by G. Divide both sides by 4 pi squared. Okay, and we're solving for L. So 1 squared times 9.81 divided by 4 pi squared should give us the length of that pendulum. Okay, so 1 squared is 1, so I'm not going to bother to put the square on there, times 9.81, okay, divided by 4 pi squared. Okay, so we're looking at about a 25 centimeter long pendulum. Okay, everybody all right with that? So that would be, if we had, I don't know, I'm going to guesstimate, that's about 25 centimeters. Okay. It takes about 1 second for it to make one full, so go from here all the way to there and back. Okay. That's pretty reasonable. Okay, questions on that one? Okay. Try this one. Okay, future astronaut lands on a planet with an unknown acceleration due to gravity. That would be a neat trick. I don't know how you would land on a planet without knowing what its acceleration due to gravity would be, but we'll pretend. Okay. She finds that a pendulum with a length of 0.65 meters has a period of 2.8 seconds. Calculate G on that planet. Okay, so on this one here, we're given the length, okay, 0.65 meters, and we're told the period, 2.8 seconds. All right, so T equals 2 pi times the square root of L over G. We're trying to find G, square everything, 4 pi squared L over G, and then just swap the T squared and the G. So G will equal 4 pi squared times L over T squared. Okay, so 4 pi squared times 0.65 meters divided by 2.8 squared. Whoops. That's not what I'm going to do. Divided by 2.8 squared. Okay, so the acceleration due to gravity on that planet is 3.27 meters per second. Actually, we only have 2 significant digits, so 3.3 meters per second squared. Which planet in our solar system would that be? Mars. Yep. Mars has an acceleration due to gravity of 1/3 of Earth. Okay, so all those scenes you saw in The Martian of Mark Watney walking around looking pretty normal, okay? It's a little hard to actually fake a different acceleration due to gravity unless it's 0, okay, on another planet, because you just things just don't fall like that. And when you slow it down into slow motion or something like that, it looks off. Okay, and of course then people's speech doesn't look right either. So those parts were difficult to fake. And if you ever looked at how things fell and stuff like that, they fell at 9.81. Okay, like you could just see things in that movie that they were harder for them to fake. Okay, just because gravity doesn't scale. Okay, all right. Any questions on those ones? Okay, I'm going to have you do a few from the workbook. I'll put them up here on the board, and we'll kind of see where we're at after that. So, okay, so from this sheet here, I would like you guys to do numbers 3, 5, 3, 5, 6. 10. 13, 14, 15. Okay, so 3, 5, 6, 10, 13, 14, 15. I don't think that'll take you that long. Okay, there's probably only one in there that'll be at all tricky. Okay, I'll scroll it up in a few minutes, okay, so you guys can see the other ones. All right, so on 13, okay, we're trying to find what G is, okay, and we know the length, 0.75 meters, and we know the frequency, 0.57 hertz. So the first thing we've got to do is get the period by going 1 over F, so 1 divided by 0.57. Okay, so there's our period, 1.75 seconds. Keep all the decimals. Okay, so we've got everything we need there. T equals 2 pi times the root of L over G. Okay, and we're trying to find G, so square everything. T squared is 4 pi squared times L over G. Okay, bring G over here. Divide both sides by T squared. Okay, and so what we should have is G equals 4 pi squared, okay, times 0.57, no, sorry, 0.75. Okay, divided by 1.75 squared. Okay, so 4 pi squared times 0.75, okay, divided by that number squared, 9.61. I wonder if it's the 2 squared times pi squared instead of 4 pi squared. I don't think you were doing anything different than what I was doing, except for that on my calculator. Because I got 29.6 and you had 22, right? Okay, any other ones giving us trouble, guys, we want to go over?
6.
6? Okay. Okay, so in number 6, we are told the mass, okay, so 0.40 kilograms, okay, and we're told the frequency is 1.0 hertz. Okay, I need period. If the frequency is 1 hertz, what's the period? 1, yeah. Okay, so I got that. So we want to find the frequency of the vibration of the second mass. So this is like situation 1, okay? And then in situation 2, the mass is going to be 0.80 kilograms. And then we're looking for frequency on this one. Okay, what can I find that's the same in both situations using the first?
Gravity.
Oh, this is a mass on a spring, so gravity doesn't matter on this one.
The spring constant.
The spring constant, same spring in both situations, right? So if I can find K using situation 1, I have that number for situation 2, and then I can find the period and go 1 over that. The trick here is to realize it's the same spring, okay? So T equals 2 pi root m over K, right? So if we square everything, we're going to have K equals 4 pi squared times m over T squared. So 4 pi squared times 0.4 kilograms divided by 1. Okay, so 4 pi squared times 0.4. Okay, that's our spring constant, 15.8. Okay, so that one I can carry over to here. Newtons per meter, and now I can find period. Okay, so that'll just be 2 pi times the root of m 0.8 over k, the 15.79. Oh. 2 pi times the square root of 0.8 divided by that number. Okay, so that gives me the period, and then I have to go 1 divided by that number to get the frequency, so 0.71 hertz. Okay, any other ones giving us trouble there, guys? How many people have done all? Okay, keep working if you're not.